Welcome to your quiet corner of cosmic discovery. I'm here to share something genuinely fascinating about our universe at just the right volume for drifting off. You know what's fascinating? I've been thinking about how something as simple as keeping track of time actually changed the way we live in such a quiet, powerful way. There's something remarkable about how humans learned to measure time, not just by the sun or the stars, but through clever inventions that helped us understand our days and nights better than ever before. I can't wait to share some of those moments with you tonight where science and daily life come together in ways you might not expect. If this peaceful blend of science and serenity helps ease your evening, consider joining our community of gentle learners. Share your favorite moment of scientific awe in the comments. First, let's create the perfect space for learning. Cocoon yourself in comfort, release any lingering tension, and let your breath become soft and steady. Beneath the quiet hush of dusk, when the world is neither fully lit nor fully cloaked in darkness, there is a peculiar moment, a twilight, when shadows stretch long and thin across the earth. It is in these gentle transitions, the fleeting times between day and night, that humans have always found themselves most attuned to the passage of time. Long before the tick of a clock or the luminous glow of a digital display, there was only the language of light and shadow, the silent dance between sun and earth that marked the slow, dependable rhythm of existence. Picture an ancient clearing, thousands of years ago, where the last rays of the setting sun spill through the branches of towering trees. Here, a group of people gathers, their faces lit with the soft gold of evening. They have no watches, no calendars. Instead, they watch the sun's descent, tracing its arc with their eyes and marking its disappearance behind the western hills. It is a ritual as old as humanity itself, to measure life not in minutes or hours, but in the changing of the sky. The oldest timekeepers were not machines, but the heavens themselves. The sun, with its unwavering habit of rising and setting, became the primordial clock. At dawn, the world was renewed. At noon, it paused in the brilliance of midday. At dusk, it slipped gently into repose. Shadows, too, became silent messengers. To the keen observer, the length and angle of a shadow on the ground told the story of the hour, a tale written in contrast and absence. In the dry, sun-scorched lands of ancient Egypt, obelisks stood as sentinels, their tall forms casting sharp lines across the desert sand. These monoliths were more than monuments. They were solar timepieces, their shadows creeping slowly along marked paths to indicate the passage of the day. The earliest sundials, simple sticks or stones planted in the earth, transformed the ephemeral play of light and dark into a predictable pattern. Time, once an abstract flow, now revealed itself in the tangible world. Yet time was never merely a scientific matter. It was a force that shaped myths and kindled the imagination. To the Greeks, time was personified in Kronos, the shadowy, ancient titan who fathered the gods. Kronos was depicted as an old man with a scythe, a symbol both of the harvest and of the inevitable cutting down of life. In myth, he devoured his own children to prevent any from usurping his throne, a haunting metaphor for the relentless consumption of the present by the future. Kronos, and later his Roman counterpart Saturn, haunted the edges of human awareness, embodying both the cruelty and the mystery of temporal passage. Across the world, in the dense jungles and highlands of Mesoamerica, the Mayans gazed skyward with equal awe and curiosity. They devised a calendar of astonishing precision, tracking the cycles of the sun, the moon, and the stars with a mathematical elegance that still impresses modern scholars. The Mayan long-count calendar did not simply measure days, but epochs, great cycles of creation and destruction woven into a cosmic tapestry. For the Mayans, time was not a straight line, but a series of repeating patterns, a wheel turning through birth, death, and rebirth. By night, when the sun had surrendered the sky, the moon and stars took up the work of marking time. The phases of the moon became a natural calendar governing planting and harvest, ritual and rest. In Polynesian cultures, navigators charted their course across the vast Pacific by the stars, reading the heavens as both map and clock. The night sky, with its steady procession of constellations, became a living archive, a memory of seasons past and a promise of those yet to come. In these ancient ways, time was felt as much as it was measured. It was a presence, sometimes comforting, sometimes threatening, always profound. Yet, as societies grew and life became more complex, the need arose for ever more precise instruments. Water clocks dripped and sand flowed, marking hours in the stillness of temples and courts. Eventually, mechanical clocks ticked their way into town squares and monasteries, dividing the day into smaller and smaller increments. The dance of shadows gave way to the relentless march of gears and hands. But even as the science of timekeeping advanced, the old awe lingered. The shadow of Kronos, the elegance of the Mayan calendar, the poetry of star-guided journeys, these lived on, not only in memory, but in the stories we tell ourselves. And in the modern era, a new kind of myth emerged, the dream of travelling through time itself. From the earliest fairy tales to the most sophisticated science fiction, humans have long wondered, what if we could slip beneath the fabric of the moment, step backward into the past or forward into the unknown future? The idea is seductive, a tantalizing rebellion against the strictures of Kronos, the inexorable flow of sand through the hourglass. In the flickering blue glow of a movie screen, time travel came alive for millions. Back to the Future, with its gleaming DeLorean and its impish inventor, invited audiences to imagine the chaos and the wonder of rewriting history. Marty McFly's journey through the decades was filled with paradoxes. Would saving a parent alter one's own existence? Could a single action ripple through time, reshaping destinies? Such questions, though playful on the surface, tapped into deeper philosophical anxieties about causality, fate, and free will. Later, in Christopher Nolan's Interstellar, time became a labyrinth, folded and stretched by the gravities of black holes. Here, time was not merely a line, but a landscape, warped by the very mass of the cosmos. Hours on a distant planet became years back on Earth. Moments lost could never be regained. The film's climax, set within the abstract geometry of a tesseract, suggested that time might be navigable, even malleable, if only we could perceive its true dimensions. The narrative was as much about love and memory as it was about physics, a reminder that time, for all its cold regularity, is experienced most deeply through the heart. Yet, for all the wild imaginings of fiction, the reality of timekeeping remains stubbornly earthbound. Our best clocks, whether the resonant ticking of a cesium atom or the optical flutter of a laser, do not leap backward or forward. They measure, they do not travel. Timekeepers, whether made of stone, water, or silicon, are rooted in the relentless regularity of cycles. Each tick is a small death, a letting go of the moment before. Still, the stories endure because they speak to a longing at the core of human consciousness, the desire to master time, or at least to understand it. We build monuments to outlast us, calendars to bind us to the past and future, stories to slip through the cracks in the present. In every culture, the act of measuring time is an act of defiance against the void, a refusal to accept oblivion without a fight. Consider for a moment the ancient watchfulness of those who first marked the solstices. Standing on windswept moors or in the depths of forested valleys, they arranged stones or carved lines in the earth to catch the earliest sunbeams of winter or the last rays of summer. These alignments speak not only of practical need, the tracking of seasons for planting or migration, but also of reverence. The turning of the heavens was a drama in which all life participated, a cosmic dance both beautiful and terrifying. Even today, the solstices and equinoxes carry a weight that is more than astronomical. Across the world, people gather to watch the sun rise through ancient doorways or to light bonfires that chase away the longest night. The measurement of time becomes, in these moments, a communal act, a recognition that we are all bound together in the turning of the earth. And yet, as the world has grown more connected, the old rhythms have been overlaid with new ones. The global positioning system, orbiting far above, synchronizes the clocks in our phones and computers to within billionths of a second. The network time protocol, invisible and silent, pulses through fiber optics and satellites, bringing order to the chaos of modern life. We live in a world where time is increasingly abstract, measured not by the rise and fall of the sun, but by the oscillation of atoms and the precision of algorithms. Still, the dance of shadows persists, if only in memory. A child watching the slow movement of a sundial, an astronomer charting the return of a comet, a poet counting the phases of the moon, all are heirs to a tradition as old as humanity itself. The old stories, too, continue to shape our dreams. In them, time is never merely a number, but a force to be bargained with, a mystery to be solved, a river to be crossed. The myth of Kronos, the careful geometry of the Mayan calendar, the playful audacity of Hollywood's time machines, each is a lens through which we glimpse the enormity of time's power and the fragility of our own place within it. These tales linger in the twilight, where the boundaries between science and story blur, and where the questions are more important than the answers. So the twilight lingers, shadows lengthen, and somewhere in the quiet space between day and night, the ancient dance of time continues. The sun dips below the horizon, and the first stars prick the indigo sky. In the hush that follows, the mind drifts to other possibilities, to other ways of measuring the immeasurable, to the secrets held in the darkness beyond the reach of shadow. The story of timekeeping is far from finished. Its next steps are hidden in the quiet hours, waiting for those who would listen to the silence, and perhaps find a new way to mark the turning of the world. And so the chase for the elusive second begins, a pursuit that winds and twists through the corridors of human ingenuity, spanning centuries and continents, threading together the disciplines of astronomy, physics, and engineering. The second, that slender slip of time, so easy to imagine, so difficult to define. Throughout history, civilizations have craned their necks skyward or peered into the inner workings of gears and springs, all in an effort to pin down this fleeting unit, to slice the endless river of duration into precise, manageable segments. But once you have measured your seconds, however you have chosen to define them, the next perplexity emerges. How can we agree on what those seconds mean, everywhere and for everyone? The sun does not rise at the same moment in Paris as it does in Beijing. Noon in New York is not noon in Nairobi. Even as the world shrank through travel and telegraph, the problem of synchronizing human schedules across distances grew more tangled. At first, before the railroad and the telegraph, local solar time sufficed. Each town would set its clocks by the sun's highest point in the sky. Noon was simply when the sun stood due south, casting the shadow of the church steeple directly northward. This worked well enough when journeys were slow and neighboring towns lived their lives in relative isolation. But as the world accelerated, as railways stitched together vast landscapes and telegraph wires hummed with messages, the chaos of local times became intolerable. Railway timetables in particular demanded precision and uniformity. Imagine a train leaving Boston at 10 o'clock by Boston time, but arriving in New York at a time calculated by New York's own solar noon, perhaps several minutes later or earlier by another clock's reckoning. Confusion was inevitable, accidents possible. The tides of commerce and travel demanded a new approach. Thus emerged the idea of time zones, a mathematical and diplomatic solution to the jagged puzzle of local solar times. In 1884, delegates from 26 nations convened in Washington, D.C. for the International Meridian Conference. There, they agreed to divide the globe into 24 time zones, each roughly 15 degrees of longitude wide, each anchored to a standard meridian. The prime meridian, 0 degrees longitude, was fixed at Greenwich, England, home of the Royal Observatory. From that invisible line, time zones would radiate outwards, each separated by an hour. It was an elegant compromise, but not a perfect one. Human geography stubbornly refused to bend to the straight lines of mathematics. Political boundaries, economic ties, and cultural traditions all tugged at the neat grid. Some countries stretched a single time zone across their entire territory, while others split themselves into several. China, for instance, spans 5 geographical time zones, yet enforces a single standard time, Beijing time, across the nation. The patchwork persists to this day. India, a vast land, chooses a single time zone, offset by half an hour from its neighbours. The tiny island of Newfoundland keeps its own idiosyncratic half-hour time zone, a stubborn legacy of local preference. As the world's clocks ticked in greater unison, another wrinkle emerged: the calendar. The Earth's journey around the Sun is not a tidy affair. Our planet completes one orbit in about 365.2422 days, a figure that defies neat division. The ancient Egyptians were among the first to grapple with this discrepancy, inventing a leap year system to reconcile the calendar with the seasons. Julius Caesar refined this with the Julian calendar, adding a leap day every 4 years. But even this was an imperfect fix. Over centuries, the calendar drifted out of sync with the solar year. In 1582, Pope Gregory XIII introduced a further refinement, the Gregorian calendar. Here, leap years occur every 4 years, except for years divisible by 100, unless they're also divisible by 400. This subtle correction keeps the calendar in closer step with the seasons, though not perfectly. Even today, the calendar accumulates an error of about 1 day every 3,000 years, a trivial offset for most, but a reminder that human attempts to tame time are always, in some sense, approximate. The months themselves are irregular, a patchwork inherited from Roman politics and superstition. February, with its 28 days, 29 in a leap year, remains a curiosity, the result of ancient compromises and the tangled evolution of calendars. The leap second, a modern invention, is a kind of echo of these older adjustments, an extra second occasionally inserted into the world's clocks to account for the gradual slowing of Earth's rotation, largely due to the friction of tidal forces tugging at our planet's spin. If leap years and leap seconds are the calendar's attempt to keep up with the vagaries of celestial mechanics, daylight saving time is a testament to the human desire to shape time to our convenience. First proposed by Benjamin Franklin as a way to make better use of natural daylight, and later adopted in various forms during times of war and energy crisis, daylight saving time is a grand social experiment. For a portion of the year, clocks are set forward by 1 hour, an artifice meant to shift human activity into the brighter, earlier hours of the day. The debate over daylight saving time is perennial and lively. Proponents claim it saves energy, reduces accidents, and encourages outdoor activity. Opponents point to the disruption of sleep schedules, the confusion of shifting clocks, and the questionable evidence for its benefits. Some regions have adopted it, others have rejected it. A few have implemented it and then abandoned it, only to revive it later. In this way, the politics of timekeeping are as intricate and contentious as the science. Beneath all these conventions, time zones, calendars, daylight saving, lurks a more profound and subtle challenge. What does it mean truly to measure a second? For centuries the answer was tied to the motions of celestial bodies. The swing of a pendulum calibrated to the length of the solar day, the oscillation of the Earth as it spins on its axis, the passage of the sun overhead. But the Earth is not a perfect clock. Its rotation is irregular, subject to the gentle tug of the moon, the shifting mass of oceans, the slow drift of continents. Even the most careful astronomical observations could not yield a second of unwavering constancy. By the 20th century, physicists and engineers sought a better standard. The answer lay not in the heavens, but in the infinitesimal realm of atoms. Atoms, those tiny building blocks of matter, possess their own rhythms, fiercely regular, immune to the quirks of tides or tectonics. In particular, the cesium-133 atom became the hero of this story. When energized, a cesium atom emits microwaves at a frequency as precise as nature allows. Exactly 9,992,631,770 oscillations for each second. In 1967, the world's timekeepers redefined the second, not as a fraction of the Earth's rotation or orbit, but as the duration of 9,992,131,770 periods of radiation corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. The atomic second is universal, indifferent to weather, geography, or politics. It is the heartbeat of modern timekeeping. But how does one harness the rhythm of an atom? Deep within the laboratories of national metrology institutes, atomic clocks hum with a quiet, relentless precision. Here, in dimly lit rooms, shielded from magnetic fields and vibrations, clouds of cesium atoms are cooled to near absolute zero. They are then prodded gently with microwaves, coaxed into flipping between energy states. Sensitive detectors listen for the telltale signature of the transition, tuning the microwave generator until it matches the atom's natural frequency. The resulting tick, invisible, impossibly regular, forms the basis of the world's most precise clocks. The quest for ever finer precision has spawned a new generation of atomic clocks, using other atoms such as rubidium, hydrogen, and strontium. Optical lattice clocks, which trap atoms in grids of laser light and measure transitions at even higher frequencies, promise uncertainties of less than 1 second over the age of the universe. These instruments are not mere curiosities. They anchor the world's navigation systems, synchronize networks, regulate the flow of information across continents. When you check your phone, track a package, or watch a live broadcast from another hemisphere, you are, in a sense, depending on the oscillations of cesium atoms half a world away. But atomic clocks are scattered across the globe, each humming in its own laboratory. How can we ensure that all these clocks agree, that the second in Paris is the same as the second in Tokyo or Washington? The answer is a kind of international ballet, orchestrated with digital signals and fiber optic cables. Each national laboratory submits its atomic clock data to the Bureau International des Poids et Mesures, BIPM, in Sèvres, France. There, a master algorithm blends the data, weighting them according to stability and accuracy to produce International Atomic Time, or TI. TI is not a clock in a particular place, but an ensemble average, a consensus second, forged from the rhythms of hundreds of atomic clocks worldwide. Coordinated Universal Time, or UTC, is the time standard most familiar to the world. It is TI, adjusted occasionally by leap seconds to remain synchronized with the irregular rotation of the Earth. Each leap second is announced months in advance, an event keenly watched by timekeepers and astronomers. When the moment arrives, the world's clocks pause for a heartbeat, 23:59:59 is followed by 23:59:60, the rarest of seconds, a reminder that even our most precise systems must occasionally yield to the stubborn realities of the cosmos. And yet, as precise as atomic clocks have become, a deeper challenge looms, one that emerges not from the imperfections of the Earth, but from the structure of space-time itself. In the early 20th century, Albert Einstein revolutionized our understanding of time. In his special and general theories of relativity, time is not an absolute backdrop against which events unfold, but a dimension intertwined with space, warped by motion and gravity. Consider two clocks, one at sea level and the other high atop a mountain. The clock at altitude, farther from the mass of the Earth, ticks ever so slightly faster. Gravity, in Einstein's view, bends the fabric of space-time, slowing the passage of time near massive bodies. Similarly, a clock carried aboard a swiftly moving jet lags behind its counterpart on the ground. Time, it turns out, is not a universal river flowing at the same rate everywhere, but a variable, local phenomenon shaped by speed and gravity. This is not mere theoretical fancy. The global positioning system, which guides ships and airplanes, maps and smartphones, relies on a constellation of satellites orbiting high above the Earth. Each satellite carries atomic clocks, ticking away the seconds. But because these satellites are both farther from the Earth's mass, and thus experience weaker gravity, and moving rapidly relative to the surface, their clocks tick at a different rate than those on the ground. Without correcting for the effects of relativity, the system's calculations would drift by kilometers each day, rendering it useless for navigation. And so, in the quiet hum of atomic clocks, in the careful synchronization of international atomic time, in the leap seconds and the shifting of daylight saving, we glimpse the delicate interplay between human convention and the deeper, enigmatic order of the universe. Our attempts to chase the elusive second draw us ever closer to the heart of reality, to the very fabric of space-time itself, a tapestry woven with rhythms both cosmic and atomic, with patterns shaped by gravity, motion, and the ceaseless curiosity of the human mind. Yet, for all this effort, the second remains a kind of shimmering mirage, precise yet slippery, universal yet local, shaped by our inventions, yet sculpted by the universe's immutable laws. The chase is not over. In the next stretch of our journey, we will travel even further, pressing up against the frontiers where timekeeping meets the quantum world, and where our deepest intuitions about time begin to unravel. For now, let the rhythm of the cesium atom lull you, and the quiet paradoxes of timekeeping drift through your thoughts, unresolved and ever unfolding. In the hush of the night, when the world quiets and the mind softens into the comfort of darkness, there is an old and patient rhythm that does not sleep. This is the ticking of the universe, a deep, persistent pulse that neither hastens nor lags, yet seems to slip so easily from our grasp. What is time, really, if not the most elusive current in which we live and move and measure our days? For millennia, humans have hungered to mark its flow. To tether the intangible, we built instruments and rituals, each a small anchor in the endless stream. Long before the ticking of clocks or the hum of quartz crystals, there were only the cycles of nature, the slow arching of the sun, the waxing and waning of the moon, the turning constellations overhead. Our earliest ancestors, patient as they were ingenious, watched the sky with reverence, their survival contingent on the dance of shadows and the return of seasons. On a morning thousands of years ago, a curious mind, perhaps somewhere in Babylon or Egypt or the Indus Valley, might have stood in the warming sand and driven a stick into the earth. As sunlight crept across the sky, the stick's slender shadow turned, growing shorter, then longer, tracing a silent arc. This was the gnomon, the first sundial, a simple arrangement, but profound in purpose. It divided the day into intervals, each marked by the tip of a shadow. By midday, the shadow shrank to its shortest, As the sun fell, it stretched once more. The sundial was not perfect. It slept with the night, lost itself in clouds and storms, but it was the first tool to carve time into pieces, the earliest way to say now and now and now again. The sundial's limitations hinted at the elusive nature of time. It responded to the sun, but the sun is not always where we'd like it to be. To measure time in darkness or on overcast days called for other inventions. Early water clocks, or clepsydras, offered a solution. They were simple vessels, sometimes a jar with a small hole through which water dripped or trickled. As the water level fell, marks on the vessel's side told the passage of hours. The clepsydra was independent of the sky, but its flow could vary with temperature or the shape of the vessel, so it kept imperfect time. Yet, even with these flaws, the water clock represented a powerful step. It was a recognition that time could be measured by the steady flow of something physical, water, sand, or oil, falling or trickling away. It also transformed time from a cosmic, celestial phenomenon into something tangible, something that could be carried, poured, watched, and even argued over. In ancient courts, lawyers pleaded their cases for as long as it took the water to drain from a standard vessel. In monasteries, monks prayed and worked by the hourglass, its sand marking the rhythm of devotion and labor. As centuries passed, the need for more precise and portable timekeeping grew. Civilizations flourished, cities bustled, trade routes sprawled across continents. Schedules became more intricate, navigation more daring. To move beyond the imprecision of shadows and the caprice of flowing water, inventors turned to the subtle regularity of gears, weights, and springs. Thus, the age of mechanical clocks dawned, a revolution as profound as any in history. The first true mechanical clocks appeared in medieval Europe around the 13th century. They were massive iron machines, often installed in church towers or public squares, their workings hidden from view, but their bells broadcasting the hour to all within earshot. These early clocks were powered by weights suspended from ropes or chains. The steady fall of a weight turned a set of gears, and a primitive escapement mechanism, a kind of mechanical governor, ensured that the gears advanced in controlled, regular steps. The escapement was a marvel, a device that transformed the smooth, continuous pull of gravity into a discrete ticking motion. It was the heart of the clock, dividing time into equal segments, each tick and tock a heartbeat of civilization. The earliest escapements were crude but ingenious. The verge and foliot, for example, used a horizontal bar, the foliot, that rocked back and forth, its motion regulated by a vertical axle, the verge, and two metal pallets. With each swing, the escapement allowed a gear tooth to advance, then stopped it again, marking the passage of time in audible steps. These clocks were neither small nor accurate, often drifting by minutes or more each day. Yet they changed the fabric of society. Now time could be measured even in the absence of sun or stars. Bells signaled the hours for prayers, work, and markets. Public life began to synchronize to the pulse of the machine. In monasteries and cities, the day was no longer just a progression from sunrise to sunset, but a sequence of numbered hours, each with its appointed tasks. The quest for greater accuracy drove innovation. The pendulum, introduced by Christian Huygens in the 17th century, transformed mechanical clocks once more. Inspired by Galileo's observations of swinging lamps in a cathedral, Huygens realized that a pendulum of fixed-length swings with a constant period. By attaching a swinging pendulum to the escapement, he created a clock that lost or gained only seconds each day, a vast improvement over the old weight-driven designs. Pendulum clocks became the gold standard for precision, adorning the halls of universities, observatories, and royal courts. They enabled astronomers like John Flamsteed and Edmund Halley to make ever more precise observations of the heavens, refining tables of planetary motion, mapping eclipses, and charting distant stars. The relationship between time and astronomy deepened. Observatories became not just places to watch the sky, but also the keepers of the world's most accurate clocks. Accurate timekeeping soon proved vital for navigation. At sea, determining longitude, the ship's east-west position, required knowing the precise time at a reference location, such as Greenwich, and comparing it to local noon, marked by the sun's zenith. Even a 1-minute error could mean a navigational blunder of miles. It was the clockmaker John Harrison in the 18th century who finally solved this challenge. His marine chronometers, painstakingly engineered with temperature-compensated balances and friction-reducing innovations, allowed sailors to carry Greenwich Mean Time across the oceans. The chronometer's gentle ticking became the lifeline of explorers, linking distant shores in the shared fabric of time. As centuries marched on, the march of progress quickened. The Industrial Revolution brought with it new demands for precision and mass production. The Victorian city was ruled by railways, factories, and timetables. Punctuality became a virtue, and the coordination of clocks a logistical necessity. Mechanical watches shrank, moving from tower to pocket, from pocket to wrist. Tiny springs, gears, and jewels, painstakingly assembled, kept time as men and women hurried through the new clock-governed world. But in the heart of every mechanical clock there lingered a tension, a battle against friction, wear, and the unpredictable quirks of metal and heat. The accuracy of even the finest spring-driven watches was limited by the imperfections of their moving parts. To surpass these limits, inventors sought something steadier, something as regular as the beat of the universe itself. Enter the age of crystals. In the early 20th century, scientists discovered that certain minerals, most notably quartz, could vibrate at remarkably stable frequencies when electrified. The piezoelectric effect, where crystals generate an electric current when compressed and conversely vibrate when exposed to an electric field, offered a new way to measure time. In a quartz clock, a tiny sliver of quartz is cut and shaped to resonate at a precise frequency, typically 32,068 times per second. This vibration is converted into electronic pulses, which drive a digital display or stepper motor to move clock hands. Quartz watches, first commercialized in the 1960s, revolutionized timekeeping yet again. They were cheap, durable, and orders of magnitude more accurate than their mechanical predecessors. Now, almost anyone could wear a timepiece as accurate as the great pendulum clocks of the past. The relentless tick of the quartz oscillator became the quiet background of modern life, unheard yet ever-present, governing everything from digital watches to microwave ovens and computers. Yet even quartz, with its crystalline precision, is but a shadow of the timekeeping possible at the atomic scale. Here, in the realm of the infinitesimal, atoms serve as nature's most perfect clocks. The cesium atom, for example, emits radiation at a frequency so regular that its vibrations define the second itself. In 1967, the International System of Units redefined the second as the duration of 9,992 631,770 oscillations of the microwave radiation absorbed or emitted by a cesium-133 atom as it changes between two energy states. Atomic clocks, first developed in the mid-20th century, are marvels of engineering and physics. Inside their carefully shielded enclosures, clouds of cesium or rubidium atoms are cooled, isolated, and bombarded with microwaves. When the frequency matches the atom's natural resonance, the atoms respond, and a feedback mechanism keeps the clock tuned with exquisite precision. The best atomic clocks today lose or gain less than a second over millions of years. These clocks are more than scientific curiosities. They underpin the very infrastructure of our world. The global positioning system, for instance, depends on a constellation of satellites, each carrying atomic clocks. Signals from these satellites, triangulated by receivers on Earth, allow us to pinpoint our location to within meters. Without atomic time, our maps and routes would dissolve into confusion. But the story of timekeeping does not end with clocks, however perfect. As our understanding of the universe deepened, we learned that time itself is not as absolute as once believed. Einstein's theories of relativity revealed that the passage of time depends on motion and gravity, bending and stretching under the influence of speed and mass. Time, it turns out, is not a universal river, but a local phenomenon, one that can flow at different rates depending on where you are and how you move. To test these strange predictions, scientists devised ingenious experiments. Among the most celebrated is the Hafele-Keating experiment, conducted in 1971. Two physicists, Joseph Hafele and Richard Keating, took 4 cesium-beam atomic clocks and flew them around the world on commercial airliners, first eastward, then westward. As the clocks circled the globe, they experienced both the effects of speed, special relativity, and altitude, general relativity. Upon their return, the traveling clocks were compared to identical ones left at the U.S. Naval Observatory. The results were astonishing, yet precisely as Einstein had predicted. The eastward flying clocks, moving in the direction of Earth's rotation, and thus traveling faster relative to its center, lost a few dozen nanoseconds compared to the clocks on the ground. The westward clocks, moving more slowly relative to the center of the Earth, gained time. The difference was tiny, but measurable, proof that time, as measured by the best tools humanity had devised, could be stretched and squeezed by motion and gravity. With each advance in timekeeping, we peel back another layer of the universe's mystery. Our clocks, once humble sticks in the sand, now taste the vibrations of atoms and the curvature of space-time itself. Yet for all our ingenuity, we are still creatures of curiosity, watching the shadows fall, listening to the tick and tock, and wondering what deeper rhythms remain, waiting in the dark, just beyond our grasp. As you rest, imagine the silence of a laboratory at night, where the only sound is the steady hum of an atomic clock, counting out the seconds with relentless precision. Time slips forward, measured and unmeasured, while the universe continues its patient ticking. But in some of the newest laboratories, a new breed of clocks that use not microwaves, but the delicate pulses of visible light, are being tested. They promise even greater precision, and perhaps new insights into the very nature of the ticking universe. Time flows, constant and unyielding, yet elusive as mist. It is the silent symphony that underpins all of existence, a melody so subtle and all-pervading that it is easy to forget it is there, threading through every moment, every heartbeat, every flicker of thought. Tonight, let us linger on the edge of this profound current and gaze into its depths, not as physicists or engineers, but as wanderers, as poets, as listeners who sense the music but cannot quite name its tune. In the hush of the night, when the world slows and shadows lengthen, you might feel time most acutely. It settles around you, a gentle pressure, whispering in the ticking of clocks and the measured beating of your heart. But what truly are we measuring when we speak of time? Why does it matter so deeply to us that we invented sundials, water clocks, hourglasses, and atomic oscillators to keep its cadence? Perhaps it is because from the very beginning humans have been creatures of rhythm. Long before cities rose or languages flowered, our distant ancestors marked the passage of days and seasons, the waxing and waning of the moon, the slow migration of shadows, the blossoming of spring and the hush of winter. All these were signposts in the wilderness, tokens of change and return. To measure time was to find one's place in the world, to anticipate the hunt, the harvest, the coming cold. Timekeeping was survival, an anchor in the shifting currents of nature. And yet, as our tools grew more refined, as the mechanical tick of gears replaced the flow of water or the drift of sand, time became more than mere survival. It became the scaffold on which we built civilization itself. Synchronized bells called monks to prayer. Factory whistles marshaled workers by the thousands. train timetables stitched continents together. In the modern world, time is the invisible architecture that holds our days upright. It parcels our lives into hours and minutes, meetings and meals, beginnings and ends. But here, in the soft quiet before sleep, let us set aside the clamour of schedules and deadlines. Let us look deeper to the subtle ways time shapes not only what we do, but how we understand ourselves and reality itself. Consider this. Our minds, so adept at remembering and anticipating, are woven into the fabric of time. Memory stretches backward, imagination leaps forward, and yet we experience life always in the narrow slice of now. The present is a moving window, infinitesimally thin, through which the river of moments flows. All your yesterdays are held in recollection, and all your tomorrows exist in hope or fear, but it is always stubbornly now. It is a paradox as profound as any in philosophy. Why, if time is a dimension like space, are we only ever conscious of one edge of it? Why can we recall the past but not the future? Why does time seem to flow while space simply is? This question has haunted thinkers for centuries. St. Augustine, the ancient philosopher, wrote, "What then is time? If no one asks me, I know. If I wish to explain it to him who asks, I do not know." In physics, time is often treated as a coordinate, indifferent and reversible. The equations that govern the dance of particles and planets work just as well if time runs backward as forward, at least in theory. Yet, in our lived experience, time is an arrow, always pointing toward what is yet to come. What gives time its direction? Some say entropy, the slow drift from order to disorder, from possibility to inevitability. The universe began in a state of astonishing order, and every passing moment increases its randomness. A broken cup will never leap together unshattered, but a whole cup may fall, split, and scatter. The past is fixed, the future open, and we are carried from one to the other by the relentless current of entropy, the so-called arrow of time. But the more we learn, the stranger time becomes. Einstein taught us that time is not absolute, but stretches and shrinks depending on speed and gravity. A clock on a mountaintop ticks just a little faster than one at sea level. An astronaut circling the Earth ages a fraction of a second less than those left behind. Time, it seems, is woven into the fabric of space itself, warping and bending with mass and motion. And yet, for all its malleability, time remains our constant companion. We measure its passage, not for the universe's sake, but for our own. In a sense, every act of timekeeping is an act of meaning-making, a way to inscribe purpose and structure onto the endless unfolding of experience. Why do we measure time? Perhaps it is because deep down we sense the fragility and beauty of each moment. To measure is to notice, to give weight to what might otherwise slip by unnoticed. The tick of a clock is a reminder that this instant, this breath, this heartbeat is unique and will not come again. In marking time, we honor the impermanence that makes life precious. There is a kind of poetry in the units we choose. A second, born from a division of the day, now defined by the vibrations of a cesium atom. How remarkable that something so fleeting and abstract can be so precisely counted. A minute, an hour, a year, each is a vessel for memory and intention. Birthdays, anniversaries, New Year's Day, these are more than dates on a calendar. They are rituals that bind us to one another and to the great cycles of nature. And yet, for all our clocks and calendars, time often escapes our grasp. Sometimes it races, sometimes it lingers. A moment of joy might flash by in an instant, while a period of waiting can stretch, seemingly endless. Neuroscientists tell us that our sense of time is a fragile construction, shaped by attention, emotion, and activity. When we are engrossed, hours vanish. When we are anxious or bored, seconds drag their feet. Time, as experienced by the mind, is elastic, bending to the rhythms of thought and feeling. Is time, then, a purely human construct? Or is it a fundamental property of the universe, existing whether or not we notice it? The answer, perhaps, lies somewhere in between. The universe, it seems, does not need a clock to unfold. Stars are born and die, galaxies spin, atoms decay, all without the aid of a watchful eye. But meaning, that fragile, shimmering thread that ties events together, is something only conscious beings can spin. Time, as we know it, is both discovered and invented, a partnership between the external order of the cosmos and the internal order of the mind. In this quiet hour, let us think for a moment of the cosmic scale of time. Imagine an ancient forest, trees rising and falling over centuries. Imagine the slow crawl of continents drifting over millions of years. Imagine the age of the universe itself, nearly 14 billion years, a span so vast that even the oldest human civilizations are but a single heartbeat. On this scale, what is a second, a minute, an hour? A single second is to the age of the universe as a breath is to a mountain, and yet every moment, however brief, contains within it the fullness of possibility. The universe, in its grandeur, is made of moments just like this one, stacked end to end, a mosaic of no's. Time, on the cosmic stage, is both a vast expanse and a series of tiny, luminous points. The life of a star, the dance of a planet, the flicker of a thought, all are woven together by the thread of duration. Our clocks, humble as they are, echo the grand cycles of the heavens. The ancient Egyptians aligned their temples to the rising of Sirius, marking the start of the Nile's flood. The Maya built their pyramids to track the motion of Venus. Even today, our most precise clocks are set by the rhythms of atoms, those tiny, ceaseless metronomes that tick at the heart of matter. And so, as you lie here, let your mind drift through the symphony of time. Feel its pulse in your veins, its hush in the darkness. Think of all the ways time touches your life, not just in the appointments and alarms, but in the quiet growth of understanding, the slow deepening of friendship, the gentle fading of sorrow. Each of these is a measure of time, not counted by clocks, but by the heart. It is tempting sometimes to wish that we could step outside of time, to linger in the sweetness of a moment, or to leap ahead to a longed-for future. But perhaps the true gift of time is not in its measurement, but in its flow. To be alive is to be carried forward, always, never able to turn back, but always able to begin again. The mystery of time remains, shimmering at the edge of understanding. Science may measure its passage with exquisite precision, but it cannot tell us what time feels like, or why it matters. For that, we must turn inward, to the quiet places where memory and hope meet, where the music of the universe becomes the music of the soul. There are questions that remain unanswered and perhaps unanswerable. Is time a river or an illusion? Does the future already exist, waiting to be discovered, or do we create it with every choice, every heartbeat? Can we ever truly know what it means to be in time rather than simply moving through it? As you close your eyes, let these questions linger. Let them settle softly, like dust on an ancient clock, in the corners of your mind. Time will carry you onward, as it carries all things, but tonight you can listen to its music, gentle and unhurried, and know that you are a part of its endless, silent symphony. And in that hush, you may find a kind of peace, not in the answers, but in the wonder. For as long as there are hearts to beat, minds to remember, and dreams to chase, the symphony of time will go on, weaving its mystery through the darkness and into the dawn. And somewhere, in the gentle space between seconds, another question stirs, waiting to be heard. As our journey through the science of timekeeping gently drifts to a close, we watch the moments slip by like a comet tail fading into the hush of space. May your thoughts wander peacefully among the stars, and when you're ready to explore more Dreamtime tales, we'll be here, patiently waiting to drift with you once again.